preparing for a nuclear engineering interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What does it mean for a nuclear reactor to be subcritical, critical, or supercritical? Criticality means the neutron population is steady from one generation to the next. If K effective is less than 1, the reactor is subcritical and power decreases. If it equals 1, power is stable. If it is greater than 1, power rises. I would also mention delayed neutrons because they make reactor control practical. Operators manage reactivity using control rods, soluble boron, moderator temperature effects, and fuel burnup compensation. While answering, focus on neutron population behavior, effective multiplication factor T effective, delayed neutrons, reactivity control, and why controlled criticality is normal operation rather than an unsafe condition. Question 2. How do control rods regulate reactor power, and what materials are commonly used? Control rods regulate power by absorbing neutrons before those neutrons can cause additional fissions. Inserting rods adds negative reactivity and lowers power. Withdrawing them adds positive reactivity and raises power. Common absorber materials include boron carbide, hafnium, cadmium, and silver indium cadmium. In a good answer, I connect this to safety. Rods must provide enough shutdown margin under worst-case conditions, including cold moderator and maximum excess reactivity. Make sure to cover neutron absorption, insertion and withdrawal effects, shutdown margin, worth of control rods, and absorber materials such as boron, cadmium, hafnium, and silver indium cadmium alloys. Question 3. What is the role of a moderator in a thermal nuclear reactor? A moderator slows fast fission neutrons to thermal energies, where many fuels, especially uranium-235, have higher fission probabilities. The key is to slow neutrons efficiently without absorbing too many of them. Light water is common but absorbs more neutrons than heavy water or graphite. Heavy water gives excellent neutron economy, while graphite supports different reactor designs. I would also discuss moderator temperature effects, because they strongly influence reactor stability and feedback. In your answer, talk about slowing fast neutrons, scattering versus absorption, moderator choices, neutron economy, temperature coefficients, and differences among light water, heavy water, and graphite-moderated systems. Question 4. How would you explain decay heat, and why is it important after reactor shutdown? The engineering problem is simple. Even after fission stops, the core still produces heat. That heat comes mainly from radioactive decay of fission products. Immediately after shutdown, decay heat is a meaningful fraction of prior power, then it decreases over time. If cooling is lost, temperatures can still rise enough to damage fuel. That is why reactors rely on residual heat removal systems, emergency core cooling, backup power, and passive heat removal features. Be sure to mention fission product decay, residual heat fraction after shutdown, emergency core cooling, loss of coolant scenarios, heat removal pads, and why shutdown does not mean heat generation stops. Question 5. What are the main differences between a PWR and a BWR? A pressurized water reactor keeps primary coolant under high pressure so it does not boil in the core. Heat transfers through steam generators to a separate secondary loop. A boiling water reactor allows water to boil directly in the reactor vessel, and that steam drives the turbine. PWRs isolate radioactive primary coolant from the turbine system, while BWRs have simpler steam generation but more direct integration. Both use water as coolant and moderator, but their layouts differ significantly. While answering, compare coolant pressure, steam generation, reactor vessel conditions, primary versus secondary loops, turbine contamination considerations, control methods, and operational complexity in pressurized water and boiling water reactors. Question 6. How do you approach radiation shielding design for a nuclear facility? I start by identifying the radiation source, alpha, beta, gamma, neutron, or mixed fields. Shielding depends heavily on that. Dense materials like lead or steel work well for gamma rays, while hydrogen-rich materials such as water, polyethylene, or concrete help slow neutrons. Then I evaluate dose limits, occupancy, geometry, streaming paths, and buildup. In practice, I combine hand calculations with tools like MCNP, scale, or deterministic transport methods, then validate assumptions conservatively. Make sure to cover radiation type, source strength, attenuation, time-distance shielding principles, material selection, buildup factors, dose limits, streaming paths, and verification through calculations or transport codes. Question 7. What does ALARA mean, and how would you apply it during plant maintenance? ALARA means keeping radiation exposure as low as reasonably achievable, not just below regulatory limits. During maintenance, I would reduce dose through detailed work planning, shorter exposure time, increased distance, temporary shielding, and contamination controls. For high-dose jobs, I would use mock-ups, pre-job briefings, remote tools, and real-time dosimetry. The practical point is balance. We reduce dose intelligently without creating bigger industrial, quality, or operational risks. In your answer, emphasize dose minimization, planning, time, distance, shielding, contamination control, work permits, dosimetry, mock-ups, job briefings, and balancing safety with practical operational needs. Question 8. What are positive and negative temperature coefficients, and why do they matter for reactor safety? Temperature coefficients describe how reactivity changes as reactor temperatures change. A negative coefficient means rising temperature reduces reactivity, which naturally pushes power down. That is desirable because it gives inherent stabilizing feedback. Fuel temperature feedback is driven largely by Doppler broadening in uranium-238 resonance absorption. Moderator and void coefficients depend on reactor design. I would stress that a reactor with strong negative feedback is easier to control and generally safer during transients. Be sure to discuss reactivity feedback, fuel temperature coefficient, moderator temperature coefficient, Doppler broadening, void coefficient, inherent stability, and why negative feedback is preferred in power reactors. Question 9. How would you analyze a loss-of-coolant accident at a high level? For a LOCA, I first define the break size, location, initial plant conditions, and safety system availability. Then I track coolant inventory, pressure changes, core uncovery, fuel temperature, and decay heat removal. Emergency core cooling performance is central. Injection, reflood, and long-term recirculation must protect the core. I would evaluate peak cladding temperature, oxidation, hydrogen generation, and containment pressure. The analysis usually uses conservative assumptions to demonstrate regulatory acceptance criteria are met. While answering, outline initiating event identification, coolant inventory loss, pressure response, core heat up, decay heat, emergency core cooling actuation, containment response, acceptance criteria, and conservative safety analysis assumptions. Question 10. What is neutron flux, and how is it used in reactor analysis? Neutron flux is the number of neutrons crossing a unit area per unit time, and it drives reaction rates in the core. Higher flux generally means more fissions and higher power, but the spatial and energy distribution matters. Engineers use flux to calculate power peaking, fuel burnup, activation, and detector response. In interviews, I connect flux to macroscopic cross-sections. Reaction rate equals flux times macroscopic cross-section, which links neutron behavior to engineering performance. Make sure to cover neutron density, velocity, reaction rates, spatial and energy dependence, flux shaping, power distribution, detector measurements, and how flux links nuclear physics to thermal power. Question 11. How do burnup and fuel enrichment affect reactor operation? Fuel enrichment sets the initial amount of fissile uranium-235, while burnup measures how much energy has been extracted from the fuel. As burnup increases, fissile material is consumed, fission products accumulate, and reactivity changes. Some plutonium forms and contributes to power, but poisons like xenon and samarium reduce reactivity. Higher enrichment can support longer cycles, but it affects licensing, economics, and safety margins. Good fuel management balances performance, limits, and cost. In your answer, mention fissile content, energy extracted per fuel mass, reactivity swing, fission product poisons, plutonium buildup, cycle length, fuel management, safety margins, and economic trade-offs. Question 12. What is xenon poisoning, and how can it affect reactor power maneuvers? Xenon poisoning comes from xenon-135, a very strong neutron absorber. It is produced directly from fission and indirectly from iodine-135 decay. At high power, neutron flux burns xenon out. After shutdown, burnup stops, but iodine continues decaying into xenon, so xenon concentration can peak. That can prevent restart or complicate power changes. Operators manage it with reactivity margin, control rod strategy, soluble boron adjustments, and careful timing of maneuvers. Be sure to cover iodine-135 decay, xenon-135 absorption, flux dependence, shutdown xenon peak, power oscillations, operator strategy, and why xenon behavior is important after load changes. Question 13. How would you evaluate whether a reactor coolant pump is performing adequately? I would compare measured pump performance against its design curve: flow, head, motor current, vibration, and temperature. Then I would check system conditions such as suction pressure, net positive suction head, valve position, and coolant density. Cavitation, seal degradation, bearing issues, or fouling can show up as abnormal vibration or reduced flow. The nuclear safety link is core cooling. Inadequate pump performance can reduce thermal margin, so trends matter as much as single readings. While answering, discuss flow rate, differential pressure, pump curves, vibration, seal performance, motor current, temperature, cavitation margin, NPSH, system resistance, and impact on core thermal limits. Question 14. What are the key concerns when selecting materials for reactor core components? Core materials must survive a harsh mix of neutron irradiation, high temperature, corrosion, and mechanical stress. For fuel cladding, zirconium alloys are common because they have low neutron absorption and good corrosion resistance in water reactors. But irradiation can cause embrittlement, swelling, creep, and dimensional changes. I would also consider activation products, coolant chemistry compatibility, thermal conductivity, and accident behavior. Material selection is always a trade-off between neutronics, thermal performance, reliability, and manufacturability. Make sure to include neutron irradiation damage, corrosion, swelling, embrittlement, creep, thermal conductivity, activation, compatibility with coolant chemistry, mechanical strength, and behavior under accident temperatures. Question 15. How do probabilistic risk assessment and deterministic safety analysis differ? Deterministic safety analysis asks whether the plant can handle predefined accident scenarios using conservative assumptions and acceptance criteria. Probabilistic risk assessment asks how likely different accident sequences are and what their consequences could be. PRA uses event trees, fault trees, failure probabilities, and metrics like core damage frequency. I would not treat them as competitors. Deterministic analysis protects against design basis events, while PRA helps prioritize risk-significant systems, human actions, and operational improvements. In your answer, compare rule-based conservative scenarios with probability-based risk insights, event trees, fault trees, core damage frequency, defense in depth, regulatory use, and how both approaches complement each other. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.